Just take a look around you for a second. Seriously, the device you're on right now, the food you ate for lunch, even the very air you're breathing out, it all comes back to one single incredible element. Today, we're diving into the story of the ultimate building block, carbon.
So let's kick things off with a little riddle. What in the world connects you, a super hard diamond, and the gasoline that powers a car? I mean, on the surface, they seem like they couldn't be more different, right? But deep down, chemically, they're all built from the exact same thing.
You guessed it, it's carbon. It's the unsung hero of the elemental world, the master architect that can build everything from the soft graphite in a pencil to the complex molecules that make up life itself.
But why? What makes it so special? How can this one element be the foundation for pretty much everything? Well, to get that, we have to first get a sense of just how essential it really is.
I mean, think about your day so far. The food you've eaten, the clothes on your back, any medicines you might take, and yeah, your own body. It's all fundamentally built on carbon structures. Every single living thing we know of is carbon-based. It's not called the element of life for nothing.
Okay, but here's where it gets kind of weird. For an element that's so ridiculously important, there's actually not that much of it. Get this, the Earth's crust is only about 0.02% carbon. In the atmosphere, just 0.03%. So how can something so rare be so important? The secret sauce is in its unique chemistry.
And that chemistry, believe it or not, starts with a problem. See, for any atom, the main goal in life is to be stable, and that usually means having a full outer shell of electrons. But for carbon, well, it's not that simple. It's got a real dilemma.
So here's the deal. Carbon has 4 electrons in its outer shell, but it wants 8 to feel complete and stable. Now, trying to grab 4 more electrons from somewhere else, that's just too much work for its nucleus to handle. But losing all 4 of its own electrons, that takes a massive amount of energy. So it's totally stuck. What does it do? It comes up with this elegant solution. It doesn't give or take. It shares.
And this whole sharing thing creates what we call a covalent bond. It's beautiful, really. Instead of one atom stealing from another, 2 atoms decide to cooperate. They share their electrons so that both of them get to have that stable, full outer shell. It's the ultimate chemical teamwork.
And you know, this is a huge difference in how chemistry works. You've got ionic bonds, like in table salt, which are all about giving and taking electrons. It's a transfer. But covalent bonds, that's carbon's specialty, it's all about sharing. And that one simple difference, it changes everything.
This sharing has some really interesting effects in the real world. So, the covalent bonds inside a carbon molecule are super strong, but the forces between different molecules, they're actually kind of weak. And that's why a lot of carbon compounds, like methane or ethanol, have really low melting and boiling points. It just doesn't take much energy to pull them apart from each other.
But this incredible ability to share electrons doesn't just solve carbon's little stability problem. Oh no, it completely transforms it into the ultimate building block, giving it what I like to call 2 chemical superpowers. Okay, so these superpowers are called Tetravalency and Catenation. I know, they sound super complicated, but trust me, the ideas behind them are actually really simple and crazy powerful.
All right, superpower number 1, tetravalency. Tetra just means 4. Because carbon shares its 4 outer electrons, it can form 4 strong and stable bonds at the same time. Think of it like a Lego brick that has connectors on all 4 sides, not just the top and bottom. It lets you build these amazing complex 3D structures, just like this methane molecule here.
Now, the second superpower, catenation. This is where carbon really shows off. It's the amazing and pretty unique ability to bond with itself over and over and over again, forming these long, super stable chains and rings. This creates a strong carbon-to-carbon backbone that's the foundation for millions and millions of different compounds.
So, you've got these 2 incredible superpowers. What can you actually build with them? Well, the answer is just about anything you can imagine, and all sorts of shapes and sizes.
Thanks to catenation, carbon atoms can link up to form these long, straight chains. Or they can form branch chains that kind of look like tiny trees. And they can even loop back on themselves to form super stable rings, like the benzene molecule you see here. The number of possible structures is just staggering.
And if you thought that was cool, it gets even more versatile. Those connections between carbon atoms, they're not all the same. They can share 1 pair of electrons, which is a single bond, or they can share 2 pairs for a double bond, or even 3 pairs for a triple bond. Each type of bond completely changes the molecule's shape and its properties, basically creating a nearly infinite chemical universe to play in.
Okay, so let's take all this amazing chemistry and see how it works in the real world. A perfect example is something you probably do every single day, washing your hands with soap.
I mean, have you ever really thought about it? Oil and water are famous for not mixing. It's like their whole thing. So how does a simple bar of soap magically make it so water can wash away all that grease and oil? The secret, of course, is a very clever carbon molecule.
A soap molecule kind of has a split personality. It's got a long tail made of a carbon-hydrogen chain, and that part is hydrophobic. That means it hates water, but it absolutely loves oil and grease. Then it's got this other end, an ionic head, that's hydrophilic. It loves water.
So when you put soap in water, these molecules do something brilliant. They automatically arrange themselves into this tiny sphere called a micelle. All the oil-loving tails point inwards, creating a perfect little trap for grease. And at the same time, all the water-loving heads face outwards, towards the water. It's like a perfect little cage for dirt.
Let's just walk through this one more time because it's so cool. First, the soap molecules swarm around a piece of oily dirt. Then, their long tails dive in and grab onto the oil. The heads then all point outwards, facing the water, forming that micelle cage we talked about. The dirt is now trapped, lifted right off the surface, and the whole thing can just be washed away by the water. So simple, but so clever.
And that really just brings it all home, doesn't it? This quote from our source material really says it all. Carbon is this incredibly versatile element that's the foundation for all life, and for so many things we use every single day.
From the brilliant sparkle of a diamond to the very code of our DNA, carbon's one-of-a-kind ability to build complex structures is behind it all, which really just leaves us with one incredibly exciting question. Since it's the ultimate building block, what amazing new materials are we going to build with it next?